The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, let's get started. I hope everybody had a great long weekend. I'm teaching today, and today we're going to be talking about transactions. Just to recap where we've been so far, Taj has sort of explained signatures in Bitcoin, in particular RSA and ECDSA, and told us a little bit about Merkle trees. And so these are some of the underlying primitives that we need to know about in order to understand how most of the blockchains today are constructed, okay? So we spent a bit of time talking about the underlying primitives. Now let's start to put them together a little bit and to understand what goes into a blockchain. So if you recall, this is a slide that Tad has shown before, and I'm really sorry about this quadrant, but I don't know, I don't think I could control this individually. So we'll definitely post the slides, of course, but let me know if something is really confusing, just raise your hand. This is something that you guys have seen before, and it's like a very sort of rough approximation of a hash chain, okay? So what we have here is this doesn't actually show the previous, but what we have here is we have some message, we have a nonce, such that when you hash these three things together, you get this hash value, which has a certain number of leading zeros at the beginning. In this case, it's 2 leading zeros. And when we construct the next block, we implicitly point to this previous block by including that hash inside of this when we produce this hash. So note that there isn't actually a physical pointer or memory address pointer type thing connecting these two things together. And note that this block does not actually contain the hash of itself. But we are sort of implicitly pointing to this by including the hash of this block in the following block, okay? And so on over here. Again, this is a different message, a different nonce, and it includes the hash of this block instead of the one before. And by including the hash of this block, it's also implicitly including the hash of this block, because that's right here. And so what we're going to see is that if you change anything about the previous blocks in the blockchain, for example, if you change this message, then you're going to need to change the nonce in order to get the hash to compute right. It's going to be a different hash, and that change is going to trickle down through the entire blockchain. And so that's what makes these things what we call tamper-proof. The fact that there are these hashes are collision resistant, and so it's very difficult. You can't really compute something else. You can't change what's in the past without having it reflected in the future. So now let's go into a little bit more detail about exactly what this message thing is, okay? We've talked about the previous hash pointers, we've talked about the nonce, we've talked about proof of work, but what actually goes inside of a block? Well, we have this general, we've kind of been alluding to it, but what goes inside a block are transactions. We're trying to build a payment system here. So what do we need to have in a transaction? What should a transaction look like? Yes?
Inputs and the outputs.
Okay, inputs and outputs. Maybe even like a higher level here, like semantically, what do we want in a transaction? Yep?
Sender, a receiver, and amount, like a message.
Okay, a sender, a receiver, an amount. Anybody else?
Transaction ID.
Okay, an ID, some way of referencing it. Anybody else? Yep.
Like a proof that it's like a legit transaction.
A proof that it's a legit transaction. Right. So exactly. So what we need is those things that you guys just said. We need to know the amount, how much of this coin we're transferring. We need to know where it's coming from, and in particular, we need an authorization of some sort that user actually authorized this spend, and we need who we're paying. And so unfortunately, this is in the dark part, but this is sort of like a little rough sketch of a transaction. And we have Alice, who's spending $5 to Bob, and we have this authorization here, okay? And this authorization, given we just learned about signatures are a great way to do authorization because it's something that only Alice can produce, right? So I don't know if you can see this, but there are question marks here. So what should Alice sign to show that she authorized this transaction? What do you think would be a good thing? What is a good message for her to sign for her to indicate her authority, her desire to produce this transaction and spend her funds?
Private key.
Her private key?
Yeah.
She should sign her private key? Okay.
Would be the whole transaction.
The whole transaction? Okay. So let's talk about signing the private key. Let's say that she did sign her private key. Okay. The problem with a signature is that in order to tell if a signature is valid, you need the thing that you signed. So she would have to include her private key, which would then share her private key with everyone, which isn't really a good way for her to use her public and private key. She could certainly sign the transaction, and the nice thing about signing the transaction, this is all blue indicating that she's signing it, is that she's signing all three of these things as well, right? She's saying, I want to pay Bob, I want to pay Bob $5. Now, what's a problem with signing the transaction? Yes?
If you just keep using it if you were Bob.
So that is an excellent point. You could keep using it if you were Bob, and we'll get into that a little bit later. But another problem here is the way that I've shown it right now, she's signing the signature. The signature is kind of part of the transaction. And so you want to make sure that you're not, when you sign a transaction, you're signing everything but the signature, right? Because you can't produce the signature. You can't sign the signature without knowing what the signature is. It would be like a whole new type of proof of work on the transaction. So I don't know if you can see this, but this says transaction minus signature. And in fact, we can even make that a little bit easier by turning that into a hash of the transaction, not including the signature. Because that sort of brings the message down to a smaller thing. And from what we know about hash functions, you can't really, given a message, and a hash of that message is difficult to produce another message that would hash to the same thing. So this hash serves as kind of an identifier for the transaction as a whole. In fact, Bitcoin uses the hash of this as the transaction ID. So this is how we refer to transactions. And it's a nice small thing to sign, which indicates Alice's intent to spend her funds. So one thing that I kind of want to go into a little bit is that there's a couple different ways for thinking about transactions and what transactions actually look like and how they're stored and how we sort of specify coins. And the most natural model to me anyway, not to everybody perhaps, is what I call the account-based model. So it's kind of like what we were doing before when we saw the banks and we were talking about banks keeping track of how much funds people have. And this is sort of how you and I might think of our own bank accounts. I think of my bank account as having a certain amount of funds in it, right? And so in the account-based model, users have certain amounts or balances associated with their usernames. And when a transaction comes in, like Alice wants to give $5 to Bob, then what might happen is that the nodes in the network, which are all maintaining sort of in a unified way this balance sheet, will end up saying, okay, Alice had 10 and Bob had 0. Alice wants to give $5 to Bob. Let's subtract 5 from Alice's account and give it to Bob. And so what the nodes would do here to see if this transaction was valid would be they would check the signature to make sure that Alice actually authorized this transaction. And they would also make sure that Alice had the funds to spend. And in the account-based model, the way that you check to see if Alice has the funds to spend is you literally look at her balance and you look at the amount she wants to spend and you make sure that if she spends that amount, the balance won't go below 0. So this is actually the model that Ethereum uses. It's not the model that Bitcoin uses. So just sort of to summarize, you store a list of accounts and balances. A transaction is valid if there's a balance in the account. And then when a transaction is processed, you debit the sender and credit the receiver. So very straightforward. Now, so like I said, this is the way that Ethereum works. And it's a little bit more natural, I think, to think about. But this is not the way Bitcoin works, actually. Bitcoin has a very different model of coins and of transactions. And I think when I was learning about how Bitcoin worked and how Ethereum worked, I found Bitcoin's model a little bit unnatural until I went through this exercise of thinking about something called replay attacks. And this is what Isan mentioned earlier, right? Which is when you have this transaction and you send it to the network and the network processes the transaction and debits Alice and credits Bob. What is to prevent a malicious agent from noticing that transaction and rebroadcasting it again to the network? So basically repeatedly debiting Alice until she doesn't have any funds left. So can you guys think of a way to maybe get around this? What would you do? How would you prevent this replay attack? Yeah.
If you can add like a specific ID to the time, for instance, in the transaction, then you can hash it.
So one thing is adding a time. Sure, time is a little bit tricky because of the nature of the system. Maybe but a time is like a pretty good idea. A unique number of some kind certainly would help, because that way, if you saw a transaction with the same number, then you'd know, okay, this transaction has been seen before. This is a repeat. This is a rebroadcast. This is not something I should process. Ethereum actually does something like this. There is sort of this number included in every transaction. But the tricky part about the way that Ethereum does this, and we're going to learn more about Ethereum later on in the course, we're going to have a guest lecturer come in and teach us about that, is that it requires you to keep track of all of the numbers you've seen. And you have to do this per user. And so all the nodes in the network have to keep track of all of the nonces that they've seen per user. And so, if a user uses Ethereum once and then goes away, all of the nodes have to keep that state forever, essentially, just in case, someone comes back and rebroadcasts another transaction. So Bitcoin, like I said, and I keep saying, does something, and there's nothing wrong with this model. We'll sort of compare and contrast. Like I said, it's what Ethereum uses. But I think that this was part of the motivation for why Bitcoin was designed the way that it was. And so Bitcoin uses this idea called unspent transaction outputs. So you'll notice, like over here, we don't have any notion of a coin per se. They're just amounts, and amounts are debited and credited. And if Alice spends to Bob and Alice spends to Carol, and they come in different orders, either one could happen first. There's no notion of like Carol gets these coins and Bob gets these coins. But Bitcoin is a little bit different. All coins are not the same. And when you're spending, you don't just include an amount, you refer back to the specific coin that you are spending. Okay, so you actually have to refer to a coin in order to spend it. And this is the really weird part. Coins are created or destroyed, consumed, and then new coins are created every transaction. Okay, so whenever you spend your Bitcoin, you have to spend it in its entirety. That Bitcoin is then destroyed, and new coins are created. And there's a rule in the entire system that a coin can only be spent once. So let's go into we'll go into exactly what that looks like in a transaction, but I want to know if there are any questions about that first, about that idea. Yes?
Aren't coins like fungible? So how would you spend, what if you spend like maybe a little bit of a coin on like some candy or something?
Yeah, that's a great question. So the question is, aren't coins fungible? So first of all, coins aren't fungible, actually. They're very specific. You can like see a coin, but you can, like the question about what happens if you only want to spend part of a coin is a great question, and we'll see how you do that in the way that the transaction is constructed. But the short answer is, if you want to spend part of a coin, you have to spend the whole coin, spend the part that you want to someone else, and then spend the rest of it back to yourself, creating a new coin in the process. Yes?
Coins are consumed and create new ones, and who will own the new ones?
Whoever you say should own the new ones. So a transaction consumes coins and creates new ones as payment. And as the creator of that transaction, as the spender, I will decide who should get the new coins. And I'll show you details of this in a moment.
So you say points, but do you actually mean like the full balance in the account, right?
No, not exactly full balance in the account. So let's go a little bit further to look at what's happening here, because Bitcoin doesn't actually keep track of balances. So let's take a look at what a transaction actually looks like, okay? So a transaction has many different parts, but we're gonna focus on two parts, which is the inputs and the outputs. And here I'm showing a transaction with one input and one output, okay? Now, an input actually refers back to another transaction's output. So let's assume, and we'll get into how this is done later, but let's assume that there are coins in the system, okay? Let's just assume that some coins have been created out of nowhere. Let's say in particular that maybe 12.5 coins have been created out of nowhere, and so there's a transaction that outputs 12.5 coins to Alice. And Alice wants to spend those coins. And so Alice would create a new transaction that points back to the transaction where she received those coins. And the way that she points back to that is using the transaction ID of the previous transaction, which you remember is just the hash, the index, meaning which output of the previous transaction she's intending to spend, and something called a script sig, which is her authorization to spend that output. So this is how Alice refers back to the output she wants to spend. And when I say coin, I'm referring to outputs, okay? So outputs can be for different amounts. Output, you could create an output. You could spend 12.5 coins and create many different outputs of many different amounts and send them to different people if you wanted to. So this is the format of a transaction. There's an input which points back to a previous transaction's output that you're intending to spend. And then the way that you spend it, you're consuming that output essentially by pointing back to it with this input. The way that you spend it is by producing a new output, okay? And again, this transaction just has one input and one output. It could have many. And the output that you produce has something called a script pub key. What the script pub key is a way of specifying the conditions under which this output can be redeemed. So in its simplest sense, you might have the script sig merely be a signature, just Alice's signature saying, I have the right to spend this. And if Alice is spending to Bob, then maybe the script pub key would actually just be Bob's public key. And the implied meaning there would be anyone who could produce a signature of the corresponding private key with that public key could then spend this output. One thing is that these two things together, the previous transaction ID and the index, serves to uniquely identify an output. So these two things uniquely identify some money to spend, okay? And the value that's specified in the output is actually specified in something called satoshis, and there are 10 to the 8th satoshis in one Bitcoin. So the value doesn't have any decimal places in it. It is always an integer. An output is what I'm referring to when I say the word coin. So, questions on this sort of general setup? Yes?
Can you talk about index?
Sure. Okay, the index is, again, remember how I said there could be multiple outputs? The index simply refers to which output in the previous transaction you're talking about. Was there a question back there? Yeah.
Yeah, I'm a little bit confused about so you have one input that can generate several outputs?
Yes.
Can you provide an example?
Sure. Yes. We'll get to that in a moment, actually. But maybe I could just draw one on the board. So, so you could certainly have a transaction that has multiple outputs, okay? And so this input here would refer back to some previous transactions' outputs. And let's say that this was, for example, 20 Bitcoin, okay? Then this needs to consume 20 Bitcoin. And it can spread that 20 Bitcoin out in any way that it wants. And there's some details here that we're going to get to in a moment. But basically, you have that 20 here. You could send 5 here, 10 here, 5 here. And each of these outputs would have its own script pub key, its own rules for how to redeem it. And each output has its own amount. Yep.
It's also possible with multiple inputs.
Yes. Yeah. Yes.
So where does like the name like chain come from? Is it more like a tree or is it?
That's a good question. So if you go back to the slide where I sort of was showing, this is where the name chain comes from here. So what we're talking about right now is what goes inside each block. And what goes inside each block are transactions. So for the moment, you can pretend like each block only has one transaction in it, but a block can contain a set of transactions. But the chain part comes from how we actually chain these blocks of transactions together. Okay. So let's talk about script SIGs and script pub keys a little bit more. So script pub keys, like I said, are in the outputs, and you can think of them as predicates. So script pub keys specify a predicate on how someone can redeem this output. Okay, so remember, a transaction can have multiple inputs, multiple outputs. Each output has its own script pub key. Script SIGs, which are in the inputs, help satisfy the predicate that's specified in the script pub key. So we would have a script pub key here. And we would have a script SIG here. And this script SIG, if this is a valid transaction, would explain how to satisfy the script pub key. So the script pub key would set up a predicate on the output. The most common predicate is produce a signature and a public key that satisfies this hash. And the script SIG would provide the information necessary to satisfy that predicate. So what does it mean to have money in this system? What does it mean to be able to spend money? What does it mean for Alice to be able to transfer money to Bob? It means Alice knows some information that allows her to produce a satisfying script SIG for some outputs out there. That's what having money means. It's not an account balance. So questions on that? Because it's a little non-intuitive. But the important thing to note here is the nodes in the Bitcoin network are not keeping track of how much money you have. It's your job to keep track of how much money you have, or a wallet's job, and we'll talk more about wallets later. And the way that you do that is by knowing how many outputs there are out there that you can actually redeem, that you have the knowledge to redeem. Like I said, a transaction can have multiple inputs and multiple outputs, and each input comes with its own script SIG, and each output comes with its own script pub key. So it's not that there's one script SIG and one script pub key for the entire transaction. A transaction can actually spend multiple different outputs and produce multiple different new outputs, and these outputs could have nothing to do with each other. Here, this input might point to a previous output that Alice knows how to spend, and this input might point to a previous output that Carol knows how to spend. And you can actually combine both of those into the same transaction, assuming you can produce a transaction with the right script SIGs. Now, Alice and Carol might have to talk to each other in order to produce this transaction, because it's going to need both signatures, but they could do it.
What prevents people from sort of shuffling around and changing the outputs and inputs?
Great question. So, what prevents people from shuffling around the inputs and the outputs? Well, part of it is because this is serialized into a transaction, and that transaction is hashed, and then these signatures are on that transaction hash. Remember, we saw that from a few slides before. So if you were to flip around the order, or if you were to try to change any bits in here and change the pub key, you would end up changing the hash of the transaction, and this signature would no longer be valid. And something also that's important to note, only valid transactions get accepted to the blockchain. So all of the nodes are checking to make sure that these script pub keys and these script SIGs work out, and I'll show you the rules that they're checking in just a moment. And so if anything doesn't match, if this signature is not a valid script SIG for whatever output it's pointing to, this is an invalid transaction. No one will accept it. In fact, most nodes won't even pass it around, and it will not get into the blockchain. Or if it does get into the blockchain, all of the nodes who are following the rules of the network will ignore it. Because if a transaction is invalid, it means the entire block is invalid, and it means any chain building off that block is also invalid. So nodes that are following the rules of the network, which are these should be valid, will not listen to that and will completely ignore that entire chain. So here's another visual of sort of what it looks like to have, and this is not what the blockchain looks like. I want to be clear. The blockchain is just a set of blocks pointing to previous blocks. What we have here is more sort of like the logical representation of what a transaction looks like. So you have a transaction right here, and you have two inputs in this transaction, and the first one is pointing to the second output of this previous transaction that happened over here. So this transaction has a hash, and maybe this is the hash of the entire transaction. And so in order to spend that output over there, you specify the hash, you specify the index, so 0, 1, 2, you specify this index right here, and you provide a script sig that will validate according to whatever the script pub key is for that output. So note here, this transaction doesn't care what those outputs are at all. It's not using those. It's not looking at those. Someone else might spend those, someone else might not spend those. It's just spending this one right here. And in the act of spending this one right here, it doesn't make those other ones invalid in the simplest form. Those could still be spent by someone else. So outputs are consumed separately. So here, it's pointing to a different transaction, a transaction with this hash. And so it specifies the transaction ID, and then it specifies which output in that transaction it's spending. In this case, it's the third one, so it has index 2. And it provides a satisfying script sig for this output, which might be probably is totally different than the satisfying script sig for that output. So this is what this transaction has to specify in order to spend those outputs. And it can produce whatever new outputs it wants to produce under certain rules.
So in that example, that whole box, though, actually points to something else. That's not these two boxes on the left, right?
This box, what do you mean when you say points to?
Chain sequence.
Yeah. This is something that will be inside of the blockchain, inside of a block in the blockchain. So this doesn't actually point to anything. It contains hashes, like literally it just contains these bytes, these hashes, of the transactions that it's spending. And those are kind of like a pointer in a sense. But when it comes to the entire blockchain, this is one part of one block. Yeah, I know. Can you guys see this at all? Can you still see that or no? Okay, good. Okay, great. Yeah, you had your hand up.
In the earlier slides, you showed what a transaction looks like, and that at the bottom you had a signature, which is like
yes.
hash of transaction minus signature. Like, is that signature the same as the script?
No, that was sort of more like an idealized transaction. So this is what a transaction actually looks like.
So the script sig is still inside the transaction. So.
The script sig is inside the transaction, but when you sign the transaction, you don't sign the script sigs because the script sigs include the signature of the transaction. And it's important to note the script sig includes the signature of the transaction as a whole, not just this part of it.
This actually has led to, we're not talking about it now, but like that was sort of there's bugs involved with that point, right?
Yeah, we're not going to talk about Malibu. Okay, yes.
Yeah, what prevents two different transactions pointing back to the same output?
Great question. So, okay, I said that there's this rule that outputs are supposed to only be consumed once, but I could definitely produce another transaction which points back to that output. I could send it to the network. And what would happen is the nodes in the network, assuming they're following consensus rules, would note that this had already been spent. So if they've already seen a transaction, a valid transaction that consumes an output, they will not accept another transaction that tries to spend the same output. That's what's known as a double spend. And so all the nodes in the network together are maintaining this rule.
Isn't it going to be kind of hard to traverse backwards and figure out what's pointing to that?
Great question. Yes, this seems kind of annoying, right? Like you see this transaction and okay, there's some random bytes in here and some, a signature, and how am I supposed to figure out what this goes to, right? How am I supposed to figure out, whether this is a valid transaction, whether it's been spent or not? And the answer is that every single node is maintaining a lot of data structures in order to make this faster. And in fact, they're maintaining a data structure called the UTXO set. And I'll tell you a little bit about the UTXO set in a minute. But really, and I'll tell you how it's created in a moment. Yes?
I'm going into like transaction feeds and how these transactions translate to the blockchain itself.
Sure. So I'm not going to go into how a block is, what a block is composed of. I'm not going to go into what a block is composed of, but we will tomorrow. Yes. Yes.
Just to confirm what you asked, so script sig is not unique to the index, it's unique to the transaction.
I'm sorry, could you say, yes?
Or like, is it like unique for each index?
Yes, there's a different script sig for each input. There's a different script sig for each input, but that script sig signs most of the transaction. So the script sig, there's a different one because different outputs could have different satisfying conditions, but the script sig has to sign a message, right? Or has to produce something. Actually, we're going to go into a few specific script sigs, and I think it'll be a lot clearer exactly what this is, because it's not clear right now what goes in the script sig or in the script pub key. So this is sort of like a logical representation of what a transaction looks like. It refers to the previous transaction that it's spending from. And the important things to note here are you can spend. You don't have to spend all of the outputs in a transaction. You can just spend one. But you must consume that output entirely and produce when you produce your new outputs. And so this is what's actually, like, this is the JSON representation of a transaction in Bitcoin, okay? And so this is probably pretty hard to read, and I don't think it's worth it to try to look at everything in great detail. But when we have the slides up, you can take a look at this, and this is literally what goes inside a transaction. And there are a few fields that I'm not talking about here. One is the version, and another is the lock time. And I think when we talk, these scripts, the script pub key and script sig can actually get quite interesting and quite complex. That's what makes Bitcoin so cool. And I think when we get into that discussion about all the different things that can go into that, then we'll talk a little bit more about what lock time is. But the short answer is the lock time tells you at what point in time this transaction is valid. So until that lock time happens, the transaction is not valid and can't be included in the blockchain. So this transaction has a lock time of 0, meaning it's valid immediately and can be included in the blockchain. So here this has one input. The input has the transaction ID and the index. So that's 0, so it's spending the first output of whatever that transaction is. And it has some script sig, which is empty. And then this is the output that it's producing. It's spending 49.99 Bitcoins from that previous output, and it's spending it to a new output, and these are the rules for redeeming this new output. Let's talk about consensus rules. So I keep using the word valid, right? This transaction's valid, this transaction's invalid. And so there are these implicit rules to Bitcoin which are defined by the software, which state what makes a valid transaction or a valid block. For transactions specifically, the sum of the inputs has to be less than or equal to the sum of the outputs. So you can't create money out of nowhere. You have to actually, you can't spend more than you're putting into a transaction. And why less than or equal to? Fees, exactly. So the difference in the outputs and the inputs is implicit, and it's a fee that essentially just goes to the miner, the person who produces the block. There is one exception to this rule. It's a transaction called the Coinbase transaction, no relation to the company. It's not named after the company. I think the company is named after it. But it's the first transaction in a block, and it's the transaction that gives out the block reward. So the first transaction in a block is special. It doesn't have any inputs. or it does have inputs, but they're meaningless. And it produces the block reward. So right now the block reward is 12.5 Bitcoins. So every time a block is produced, every time someone solves that proof of work puzzle and produces a block, they include a transaction at the very beginning that usually gives themselves 12.5 Bitcoin plus whatever fees are implicit in all of the as the sum of all of the transactions in the block. So this invariant must be maintained, except for the Coinbase transaction, of which there's one in every block. And then this invariant must also be maintained, which, oh yes, sorry.
Who determines the fees?
The people creating the transaction determine the fees. So when I create a transaction, I'm specifying which outputs I'm spending and putting them in my inputs, and I'm producing the outputs. So I could, I just have to maintain that invariant, right? So let's say that I'm spending an input worth 5 Bitcoin. I could produce an output worth 5 Bitcoin, meaning that the fee is 0. It's very unlikely that my transaction would get accepted into the blockchain with a fee of 0. It's possible, sure, but if I'm not mining myself, why would a miner take my transaction when they could take a transaction that has a higher fee associated with it? And the fee is implicit. It's the difference between the sum of the inputs and the sum of the outputs.
So higher the fees is more likely that you will be processed.
Yes. Yes. Any other questions at this point?
The fee is taken out of the inputs or out of the outputs?
The fee is, okay. The fee is implicit. So in the inputs, you're consuming. So let's use this example right here. Okay. So here we're consuming this output, which has 20 Bitcoin in it, right? So implicitly, this thing has 20 Bitcoin to spend. All right. Now before I had it set up as 5, 10, 5, right? And so 20 needs to be greater than or equal to 5 plus 10 plus 5, and it is, great. 20 is greater than or equal to 20. What I could do is I could change this number to a 4. And so what this means is, notice that this adds up to 19 now. Where did that 1 Bitcoin go? That 1 Bitcoin implicitly goes to whoever produces the block in which that contains this transaction.
Greater
So
than?
it's greater than.
Greater
than. Oops.
Some of the outputs are.
No. Yeah, you're right. Sorry, that should be greater than or equal to. Sorry about that. So another invariant that needs to be maintained is that this output has not already been referenced in another transaction, in another valid transaction. And then, as I alluded to, a final invariant is around the lock time. So let's go into an example of how this actually works, this script sig and script pub key thing. So I haven't really gone into detail yet about what this is. I sort of implied that this specified a key and this specified a signature, but what does this actually look like? And I mean, I think this is really, really interesting, actually, because Bitcoin lets you specify lots of different script pub keys and lots of different script sigs. And so this gives you this kind of flexibility so that you can program in different kinds of conditions on what it takes to redeem a transaction. So we're just going to talk about a couple very simple ones, because to get into sort of more complex stuff, we need to go really deep into this word script. So basically, the script pub key and the script sig are composed of opcodes. So Bitcoin has a little less than 200 opcodes, and you write Bitcoin scripts using these opcodes. So let's talk about the most common Bitcoin script, which is pay to pub key hash. So the idea here is you want to send money to a public key. So Alice has Bob's public key, and Alice wants to pay Bob, and so Alice wants to send money to Bob's public key. Well, the reason that this is called pub key hash, public keys are kind of big, and there's this nice, you can kind of like make this nice observation that you don't necessarily have to put the whole public key in the output. You can put a hash of the public key in the output, and I think Taj already talked about this when he was talking about Bitcoin addresses. So the script pub key is instructions on how to verify a signature of a public key that has been hashed. And the script SIG is that signature and the actual public key, the preimage of the hash public key. And this is what that looks like. So this is literally the script pub key for a pay to pub key hash input or output. And this is literally the script SIG that you would use to redeem that output. So this right here would go inside one of these, and it would set the conditions under which you could redeem this output. And this right here would go inside the input of the transaction that's redeeming it. And let's take a look at how this actually works, okay? So what the Bitcoin script interpreter does is when it's evaluating whether or not a transaction is valid, it takes a look at the input, and it looks at which previous transaction it's looking at and which index the output is. And it grabs the script pub key. Well, first of all, it makes sure that output hasn't already been spent. Then it grabs the script pub key, and it takes the script SIG, and it puts them on top of each other just like this. So that's the script SIG up there. This is the script pub key down here. And then it runs this combined script through the Bitcoin script interpreter, which is based on a stack model. So it starts pushing things onto the stack. It starts at the very top, and it starts pushing these items onto the stack and evaluating them. And so the rules are that constants get pushed onto the stack, and then operations, and these things right here are operations, op dupe, op hash 160, op equal verify, and op check sig. These are all Bitcoin opcodes. Operations have different rules as to how they're evaluated and what they consume off of the stack. So the first thing is a signature. We're going to pop the signature and push it onto the stack because it is a constant. So this would be the signature that Alice might produce in order to spend her output. Then same thing with the pub key, because the pub key is also a constant. Then we're going to take this first, now, okay, we're done with constants for the moment, and the next thing on the stack is op dupe. Op dupe does basically exactly what it sounds like. It takes the thing that's currently on the top of the stack and it duplicates it. So the way that we consume op dupe is we take this pub key and we create another copy of the pub key. The next op is op hash 160. Also does exactly what it sounds like. It takes what's on the top of the stack, it hashes it, and it pushes that hash onto the top of the stack. So after we run op hash 160, this is what our stack will look like. Next thing is a constant. So we take that constant, which is which is the hash of the pub key. So this is the address that this money is being sent to, essentially. And we put that on the top of the stack, and then we run this operation called op equal verify. Whenever an opcode ends with verify, it means that it's a little bit special. It means that it has the ability to, if it fails, break out of the entire script execution and immediately cause transaction validation to fail. So op equal verify does what it sounds like. It checks to make sure that the two things on the top of the stack are equal. And if they're not equal, then it immediately fails validation. So you'll note that what the two things at the top of this, let's go back to what the two things on the top of the stack are right now, okay? So we pushed the SIG, we pushed a pub key, we duplicated that pub key, and these are from the script SIG. So this is from whoever's redeeming the transaction, okay? So whoever's redeeming the transaction has put a copy of this pub key on there, and now that pub key is on the stack twice. We hashed the pub key, and then we pushed the hash that was specified in the part of in the previous transaction that set up the rules for how to spend this, okay? And then op equal verify makes sure that these things are actually the same. And if they're not the same, then it'll fail that verify check and the entire transaction validation will abort and it's an invalid transaction. So let's assume that they're the same. Okay, great. Then op equal verify, then we continue transaction validation. And now we're left with this, op check sig, pub key, sig. And this does exactly what you think it might do. It pops two things off the stack, checks to make sure that this signature is a valid signature for this pub key, and if it is, it pushes true onto the stack. And if there is a true on top of the stack, in fact, I think it's if there's any constant on top of the stack when we've consumed all of the parts of our script sig and script pub key, then this transaction, this returns true and the transaction is considered valid. So let's, this is a lot, and I know this is kind of complicated. So let's sort of step through this one more time, and there's just a couple things that I want to make clear. This part right here is set up in the output of whatever transaction we're spending. So if Alice creates this transaction and she's spending to Bob, then Alice would put whose pub key here? Or hash of a pub key, actually. Right, so Alice would put the hash of Bob's pub key here. And when Bob's redeeming, what would go in the input that needs to redeem that output? Sorry, I can't hear. Bob's signature and the pub key that corresponds to that signature, because all we have is a hash. So those are the things that would get put on top of the stack. So up there we have Bob's signature and we have Bob's pub key. Again, those get pushed onto the stack because they're constants, duplicated, hash the top, copy over the hash, make sure that they're equal, and then check the signature. And this is a pay to pub key hash script. It is the most common script in Bitcoin. And this is basically the standard way of spending money. Are there questions about this? Yes?
Is there a significance in having their equal verify before the check sig? Because it seems like they're both verifying things, and I'm wondering.
Yeah, that's a great question. So let's say that we didn't have this equal verify here. Then what could a malicious spender possibly do?
Well, I just meant like flipping the order. Like, we're still verifying both, but if you did the check sig first versus the equal verify first, does that matter?
Oh, that's a good question. I don't think that would matter. I'm not sure. Would it matter?
You could. It's faster to verify that two hashes are equal. The check sig operation takes a lot more CPU time. So I guess the idea is if you're going to fail, fail the easy part.
Yeah. Yes?
So are all nodes on the network running this?
Yes. Every single node on the network is running the Bitcoin script interpreter inside of it. And the Bitcoin script interpreter is known as is what's called consensus critical. So if two nodes have slightly different script interpreters that would interpret this in different ways, the network would have a consensus failure. Yes?
Why not just pay to pub key?
Pay to pub key is a thing, actually. And pay to pub key hash is considered better. And the reason for that is kind of subtle, actually. It's because, so the hash of the pub key is smaller than the pub key, right? And this is definitely going on the blockchain. We don't know if this is going to go on the blockchain or not. Not all outputs are consumed. So let's put the small stuff here and the big stuff over here. It's about saving space. Also, the set of unspent transaction outputs is something that every node has to maintain. It's very important. You are referring to it quite a bit. This is not something that every node has to maintain, and so you want to make this smaller, even at the expense of making this bigger. Yes?
So then you could accidentally sign a transaction that has a public key but a script that doesn't actually verify it.
Could you accidentally sign a transaction that has a public key but a script that doesn't verify? Let me see if this answers your question. So here is an example of an unspendable output, okay? The unspendable output has an op return as the first instruction of its script pub key. Op return does what you might think it does, which means when you evaluate it, it returns immediately and says invalid. And so if you have one of these in your transaction, in your script pub key, there's no script sig that could possibly redeem the script pub key. You could create anything you wanted, and no matter what you put on there, it would never evaluate to true. There's no way to actually redeem the script pub key in this output. Does that answer your question?
I think it's the opposite. I was asking if you could accidentally get something that will always evaluate to true.
Ah, okay. Well, that's the next slide. So yes, this is what's called an anyone can spend output. Okay. The simplest anyone can spend output is just an empty script pub key, because a script sig that has opt true in it would evaluate to true. Notice here, there's no public keys, there's no signatures, there's no hashes of public keys. The script pub key doesn't actually specify any public keys. And so, but when you evaluate this right here, you'd push opt true onto the stack, and then you would finish, and there would be a true. Opt true would push a true onto the stack, and then when you finish, there would be a true on the stack, meaning this is valid.
Another way you put the opt true in the output script as well.
Yep.
And then you wouldn't have to push anything.
Yep. Yeah. So this is an anyone can spend output, and this is a no one can spend output. And there's no public keys in here. There's no signatures in there. So you can totally create outputs that have nothing to do with signatures, or maybe need to verify multiple signatures, which we're not going to go into right now, but is also possible. Yes?
Script sig can have operations in it?
Yes. Yes. Yes, it can.
But the list of operations are limited.
There are fewer than 200 opcodes. The number of standard opcodes is even smaller, meaning that there's a very small number that you can use in your script sigs and script pub keys. And it's definitely possible if you write some weird script pub key or some weird script sig to accidentally create outputs that are never spendable, or to accidentally create outputs that could be spent by someone else. So there's a standard set of script pub keys to use, and I would not recommend going outside that set, except for in the lab that you're going to do, because we have some more fun ones in there. Yes?
Could you explain a little bit more on the pay-to-script hash? And like what scenarios it's used?
Sure. Pay-to-script hash, I don't actually have slides on pay-to-script hash, so I'm not sure that we can do a good job of explaining it right now. But the idea behind pay-to-script hash is that, I don't have the slides for it, but the idea is that you're going to put, instead of this particular script pub key here, you're going to have a script pub key that includes a hash of a script, and then the script sig has to produce that script, and it has to match that hash, and the whole thing has to verify. Is the rough idea behind pay-to-script hash. And we can produce an example of that for you tomorrow. But the cool thing about that is you don't even know what you have to do to redeem this output, right? So someone has to produce a script that, when combined, that has the same hash, and when combined with the script pub key, will evaluate to true.
And that script would be pushed on the stack.
So the script sig and the script pub key literally just get concatenated together and then evaluated as one thing. So yeah, it would just go through the same thing. Any more questions? So what do you guys think? Is this good? Is this bad?
Could you try to do like a GPU less attached on the network if the transactions are never spendable but really easily dated?
Yeah, that's a great question. So the question is, could you DOS a network by creating transactions that are not spendable? You can't really DOS the network per se. So this is an example of a transaction that's not spendable. And see how it has this operator and it says whatever. There is this pattern of people who like to store things in the Bitcoin blockchain because it's there and it's very highly replicated. And so one type of transaction that a lot of people make is an operator with a hash of some data in it or some data in it. These are unspendable outputs that will live on the Bitcoin blockchain forever and will be part of the UTXO set possibly forever. Generally, Bitcoin developers discourage using Bitcoin in this way because it does bloat the UTXO set. That said, there's nothing to prevent you from doing it if you want to pay the fees. What?
It's actually not part of the UTXO set because it has the aperture.
Oh, really? I didn't know that. Okay, I didn't know that they weren't kept in the UTXO set.
Before, they would just make the pub key hash into whatever data they
Yeah.
want to put, and that would bloat the UTXO set. So
I
it's like,
see.
well, this is better.
Okay, I didn't know that those weren't included in the UTXO set, so that's good. So then it doesn't bloat the UTXO set, it just goes in the blockchain, and you paid the fee to put your transaction in the blockchain, so good for you. Yes?
So what's the architectural logic for having a specific set of opcodes that Bitcoin can run? Why not use a more general programming language? Is it just out of control?
That's a great question. So why have this weird opcode thing, right? I mean, what kind of sense does this make? So the problem with a general programming language is it's really easy to shoot yourself in the foot. It's really easy to write a program that you think, how many of you have had a bug in your program ever? Please, all of you should probably raise their hands, right? And how many of you have had bugs in your program that showed up a lot later than you thought they would when you thought your program didn't have any bugs, right? So these things, once you put them out there, these script pub keys and script hash, once you put these transactions out there, they're out there. You cannot take them back. Well, not easily. They might execute in ways that you didn't anticipate them executing. The more complicated the script you write, the more likely it is that there's some hole in your script, some way of satisfying it that you didn't anticipate that could end up stealing your money, right? So with a general programming language, well, you might think, oh, well, at least, these opcodes are super tricky and weird and I don't understand them. At least with a general programming language, I'm more likely to write correct things, right? Actually having this strange opcode language has a lot of benefits. So number one, it's not Turing complete. You know exactly how much CPU it is going to take to run these scripts because of the nature of the opcodes and the language. There's no for loops in here. You can't just run a while that takes forever. This is a stack-based language, and so it's very easy to tell how long a transaction is actually going to take to execute. And this is really important because every node in the network has to execute these things. So you don't want a script sneaking in there that's going to take hours to execute. It's also, you can look at the number of opcodes in the script and like I said, get a rough sense of how expensive it's going to be, and that's why there are limits on the number of opcodes you can have in a script. It's very difficult to do that if you have a more general programming language. So those are a couple of reasons, and I think it's important to point out that Ethereum, which does have a more general programming language, there are constantly problems popping up where people are taking advantage of contracts, even fairly well understood ones, or so-called, we thought they were well understood, and figuring out how to freeze people's funds or steal people's funds. So that's the motivation behind this sort of strange stack-based opcode language. Are there any other questions? Yeah, back there.
You talked about unspendable transactions, outputs.
Outputs, yes.
Could you comment on colored coins?
Oh, colored coins. No comment on colored coins. I don't understand them well enough to talk about them right now. Yeah. What did you?
I would just say one other thing. Most of a lot of the cool opcodes are disabled. So it's very limited. It seems like there's a list of, here's all these opcodes. Oh, I can multiply numbers together. That's disabled. It's in there.
Yeah. And I do want to stress, when you're dealing with real money, so not in the lab for this class, you want to stick with very standard scripts. You don't want to write super crazy, weird, tricky scripts. Or if you do, you want to get them vetted very carefully. Yes?
Who is disabling and enabling these things?
Great question. So there are two levels at which things can be enabled or disabled in Bitcoin. So first, there's the validation rules. So what makes a transaction valid or not valid, right? And that meaning that If a transaction is invalid and it's in a block, that whole block is invalid. If a transaction is invalid and in a block and that block is in a blockchain, that entire blockchain is invalid. So there's that level, and we're going to talk about sort of how those rules change and who sets those rules, but you can consider them sort of for now being set by the code, the Bitcoin core, or the Bitcoin software, which specifies what is valid and what is invalid. But there's another level at which you can sort of adjust what sort of ends up getting accepted or not accepted, and that is what is transmitted over the peer-to-peer network. So there are transactions that are valid but are what's known as non-standard. And that transaction, if it gets into a block, that block is still valid, but the nodes in the network, if it sees that transaction, won't relay them around. So you'd have to like be a miner and actually decide, I want this transaction in a block, and mine that block. And if you do that, everyone will consider it a valid block, okay, fine. But no one will actually send your transaction around. And so if you're not a miner yourself, the odds of it getting into the blockchain are very low. And so those are the two sets of rules. The peer-to-peer rules are more restrictive than the validation rules. Okay, so we already kind of started talking about this a little bit. What are the benefits of UTXOs and what are the downsides of UTXOs? So one of the benefits of UTXOs is that, do you guys see how they help with replay attacks? I can copy this transaction and put multiple out there, but you're only allowed to spend an output once. And once you consume that output, that's it. So you can't really do replay attacks in this model. So it's a very sort of elegant way of getting rid of the replay attack problem without having to store a nonce per account in your system. Another benefit is that you can actually get a little bit better privacy with this UTXO system because you don't have to use the same public key for all of your transactions. You can generate new ones every single time and then combine UTXOs from different things into, you're going to have to combine them anyway, even if they did spend the same public key. So why not generate fresh ones all the time? And it becomes a little bit harder to track who you're spending and who you're paying to. In the account-based model, you need to have, it's more likely that all of your funds are going to be in one account in order to make a spend. Now, a downside of UTXOs is that they're complicated. So when I first heard about UTXOs and I first understood how Bitcoin worked, I was like, why does Bitcoin work this way? This makes zero sense. An account-based model would be so much easier. And I think for wallet providers and for people who are writing user software, it is easier to deal with an account-based model than a UTXO model. Because people who are writing Bitcoin wallet software have to keep track of all of your UTXOs and then figure out how to combine them to get the amount that you want to spend and make sure that they produce what are called change outputs the right way. So you don't accidentally lose some of your money because you're spending an output that has 100 Bitcoin, but you're only paying someone 1 Bitcoin. You better make sure you have that 99 Bitcoin output in there going back to you, right? So it just makes everything a little bit more complicated. You can't just spend the amount you want to spend. You have to find these outputs and combine them in the right way and figure all of this stuff out. Another problem is around fungibility. So this is why I say that Bitcoin's not fungible, because of these outputs and the fact that you have to point back to the output that you're going to spend, which ends up creating what's called a transaction graph. So you can sort of see how things are chained together, and you can actually discern quite a bit of information about what's going on in the network. And in fact, the FBI has used the transaction graph in some of its cases around Silk Road to see where Bitcoin was moving. And there are many companies out there, Chain Analysis, Elliptic, that provide services based around the fact that Bitcoin's transaction graph is totally open, and so you can sort of see how coins are moving around. So in addition to the transaction graph problem, you kind of lose this aspect of fungibility in the sense that, let's say that I know that for whatever reason, these coins came from, let's say, a terrorist or something like that. You then know exactly where those coins are going, and you can kind of see the chain of transactions that come off of those coins. And it sort of creates a potential opportunity for someone to blacklist coins. Or you might decide that you like coins that were produced that are fresher than other coins. So there's this ability to distinguish between coins, which is a little bit troublesome because fungibility is generally considered a very good property for money to have, and this is not entirely fungible. But people are working on that. Any other questions? I alluded to this earlier, but every single node that's running the Bitcoin software keeps this data structure called the UTXO set. So these are all of the outstanding unspent transaction outputs. It's all of the coins in the system, all of the money in the system that's available to be spent. The way that this is computed is when a Bitcoin node comes online and starts to download the blockchain, they run through the blockchain and continuously add and remove things from the UTXO set to produce a UTXO set that is valid for whatever the last block is that it's seen. When a new block comes in, a node runs through the block and, again, removes and adds things to the UTXO set as necessary. Right now, there's about, 60 million UTXOs in the UTXO set. A lot of them, unfortunately, well, a lot by size, in terms of bytes of the UTXO set, a lot of them are very small and are unlikely to get spent very soon, so that's kind of a bummer. The UTXO set is about 3 gigabytes right now, I think, and so every node in Bitcoin, in addition to storing the blockchain, stores this UTXO set and uses this data structure to very quickly tell if a transaction is a double spend or not. Any questions about the UTXO set? Yes, SJ.
How do you avoid having small transactions accumulate over time?
That's a good question. How do you avoid having small transactions accumulate over time? I don't know the answer to that question. It's kind of a bummer. It's not really in people's interest to generate those transactions because you're creating, I haven't talked about how fees are computed yet, but fees are measured according to the resources that a transaction takes up in the system. Fees are measured according to the size of the transaction. So if you have to combine a whole bunch of tiny outputs in order to get a big enough sum, you're going to have to pay more in fees. So it's not really in your interest to produce a lot of these tiny things, but there's not really a good way of stopping it. And in fact, there have been services in the past, like Satoshi Dice and whatnot, that have created a ton of very tiny outputs and have bloated the UTXO set. I don't know, Taj, if you have any insight onto how to stop that from happening. Other than the fees, yeah.
Better wallet software, a lot of it's unintentional.
Yes?
You mentioned that one of the pros is privacy and the ability to generate new hotkeys.
Yes.
But what does prevent you from, in the account-based model, prevent from generating new accounts? Like what's
so I'm not sure in the account-based model, we'll find out more about this when we get to the Ethereum section of the class, how you combine spending from different accounts. But Bitcoin makes it very easy to combine spending from different pub keys. In the account-based model, I could imagine it being a slightly more complicated process. But that's a good point. Yes, you could definitely create a lot of accounts with a lot of small balance, but if you want to spend a lot, you're going to have to somehow accumulate all of that spending. Remember I talked about how there is like one special transaction in every block called the Coinbase transaction, and this transaction does not have to follow all of the rules specified before. So this is kind of like a hard-coded exception into how Bitcoin works, that there can be this one transaction in every block called the Coinbase transaction. It is the first transaction. The Coinbase transaction has exactly one input, and that input needs to have certain field. This input does not point to a previous output, okay? This input is essentially empty. This is the transaction that doles out the block reward. So this is the transaction that the block reward used to be 50 Bitcoin, 25 Bitcoins, 50 Bitcoins, now it's 12.5 Bitcoins per block. This is the transaction that doles out that 12.5 Bitcoins plus the fees of the block. So it has exactly one input, and that input has all zeros for the previous transaction ID, and then FFFFF for the index into that previous transaction ID. I think the script sig can basically be whatever you want. It's not evaluated. It might have to be valid, I'm not sure. And then its output is in Satoshis. So this is 12.5 Bitcoin, because remember, a Bitcoin is 10 to the 8th Satoshis. So this is 12.5 Bitcoin plus, here are the fees from that block. And you probably, if you're the one, so the miner is the one who creates this transaction. And the miner who creates this transaction probably wants to give themselves the Bitcoin and the block reward. And so would specify in here a script pub key that they could redeem. Note that this also has the nice property of making, well, I don't know if it's a nice property, but all the blocks that people work on are actually different, because in each block, the Coinbase transaction is going to be different because each person's trying to pay themselves for the different miners. Yes?
What's restricting them to 12.5 Bitcoins?
Ah, great question. So what would happen if a miner put like 100 Bitcoins in there? Any idea? So what's keeping that at 12.5 Bitcoins is the same thing that's keeping invalid transactions out of the blockchain, which is the consensus rules of Bitcoin. It says in the code that at this point in time, given the block height where we are, that number should be no larger than 12.5 plus the fees in the transaction. And if a miner put a different number in there, a higher, they can put a lower number, that's fine. They'll end up burning some Bitcoin, which is unfortunate, but if they try to put something higher in there, the network will regard it as invalid because the network is running a set of rules. And we are in this class going to get to what happens when you want to change that set of rules, which gets really tricky, but right now, assume that the network is running this set of rules. They're all checking, they're all validating. And so the answer is the network would reject this block if there was a higher number in there. So this is kind of fun because you can sort of put whatever you want in here. And so miners like to put advertisements in there. And there actually was a time, I don't know if you can still do this, where you could literally buy this space from miners and put whatever you wanted in there. So you could put your name or, like ask someone to marry you or whatever, you might want to do to put in the Bitcoin blockchain for all eternity. But yeah, so miners like to put fun things in the script sig, and maybe we could show them some of those things later. Or you could go look yourself.